Now let's take a look at a magnetism question from the 2008 free response section of the AP exam. This is question 3. It's a 15-point question. Some questions are worth 10 points, some questions are worth 15. A rectangular wire loop is connected across a power supply with an internal resistance of 0.5 ohms. So we've got a resistance there, 0.5 ohms, and an EMF of 16 volts. Remember, EMF and voltage are the same thing. The wire has a resistivity of 1.7 times 10 to the negative 8th ohm meters and a cross-sectional area of 3.5 times 10 to the negative 9th meters squared. When the power supply is turned on, the current in the wire is 0.4 amps. Calculate the length of the wire required to make the loop. Okay, we are looking for length of wire, and I'm going to need to use this resistance formula. I'm going to need the resistance, and I'm going to have to use Ohm's law in order to find it. I'm given the total voltage is 16 volts. I'm given that the internal resistance is 0.5 ohms, and the current is 4 amps. Using V equals IR, I can determine 16 volts equals 4 amps times resistance. The total resistance must be 4 ohms. But wait, there's an internal resistance in the power supply of 0.5 ohms. That means that the wire itself must be 3.5 ohms. I'll continue my work down here. The resistance of the wire is 3.5 ohms. The resistivity of the wire, that's rho, is 1.7 times 10 to the negative 8th ohm meters. The cross-sectional area is also given at 3.5 times 10 to the negative 9th meters squared, and I'd like the length of the wire. So I'm going to use this formula. Resistance equals resistivity times length over area. I'll plug in my values. 3.5 equals 1.7 times 10 to the negative 8th times the length over the cross-sectional area, 3.5 times 10 to the negative 9th. And when I solve this for L, I get L equals 0.72 meters. meters. Okay, what's next? The wire loop is then used in an experiment to measure the strength of the magnetic field between the poles of a magnet. A magnet is placed on a digital balance and the wire loop is held fixed between the poles of the magnet as shown below. The 0.2 meter long horizontal segment of the loop is midway between the poles and perpendicular to the direction of the magnetic field. The power supply in the loop is turned on so that the 4 amp current is in the direction shown. We can see the direction of the current here by these arrows. This is conventional current or positive charge flow. We will use our right hand to figure out anything about forces. In which direction is the force on the magnet due to the current in the wire segment? So this is asking about the force on the magnet, not the force on the wire. Now the right hand rule that we use tells us the force on the wire. Let's think about that first. We need to think about the direction of the magnetic field. The direction of the magnetic field is out of the north and into the south. We need to think about the direction of the current, and the current in this case is into the page. And now we need to determine the force on that current carrying wire. What I'm going to do is take my right hand. I'm going to put my fingers in the direction of the magnetic field, and I'm going to put my thumb in the direction of, here we go, put my thumb in the direction of the current carrying wire. And what I find is that the force given by my palm is down. Now that's the force on the wire. The force on the magnet must be equal and opposite. So my justification would consist of two parts. First, the right-hand rule tells us the force on the wire must be up. Excuse me, the force on the wire must be down. Newton's third law tells us the force on the magnet must be equal and opposite. Opposite direction. Let's look at part C. The reading on the balance changed by 0.06 newtons when the power supply was turned on. Calculate the strength of the magnetic field. What I've got here is I've got a force due to a magnetic field, and that has a magnitude of 0.060 newtons. I know the length of the current carrying wire in the magnetic field is 0.020 meters. I know the current in the wire is 4 amps. And what I would like is the strength of the magnetic field. For this I can use the formula force is equal to magnetic field times current times length. And I'll plug in my values. And when I solve for the magnetic field, I get 0.75, and the units on magnetic field are Tesla. Let's keep going. Suppose that various rectangular loops with the same total length of wire as found in Part A were constructed such that the lengths of the horizontal segments of the wire loops varied between 0.02 and 0.10 meters. Okay, what are they talking about here? They're saying that they made different loops, but that this part, this horizontal segment, varies in length. Notice that varying the length would vary, notice that varying the length of that wire would vary the force. The horizontal segment of each loop was always centered between the poles, and the current in each loop was always 4 amps. The following graph represents the theoretical relationship between the magnitude of the force on the magnet and the length of the wire. Essentially what we're looking at here is the formula that we used before, and we're assuming that these two things, magnetic field and current, are constant. Therefore, as length increases, force should increase. On the graph above, sketch a possible relationship between the magnitude of the force on the magnet and the length of the wire segment if the wire segments were misaligned and placed at a constant non-perpendicular angle to the magnetic field as shown below. Well, what this is going to do is this is going to decrease our force. If we don't have a perpendicular situation, then the force is not going to be maximized. Technically, this formula has BIL sine theta, and when theta is not 90 degrees, then we don't have a maximum force. So if the force is not maximized, we're going to see a shape that looks something like that. It's going to be a force that's less than the predicted value. Let's look at part E. Suppose the loops are correctly placed perpendicular to the field and the following data are obtained. Describe a likely cause of the discrepancy between the data and the theoretical relationship. There are two things to think about here, why the force might be less than the predicted value. And what we want to do is go back to our setup and think about this setup. What if you were trying to make a loop of wire and you couldn't make it into a perfect rectangle? Also, what if the magnetic field at the edges was not as strong as it was in the center? Both of those scenarios would decrease the force on the current carrying wire. And both of those are appropriate answers here. So, one possibility is that the loops are not perfect rectangles. In that case, if they had curved sides, the length would not be quite right, this length that we're measuring. And that length is what determines, one component that determines the force on that current carrying wire. The other problem could be that the magnetic field is weaker on the outside. I hope this helps. You can find more information about this and other AP questions at apcentral.collegeboard.com.